This angle is the angle between the magnetic field and the direction it's going. That's the instantaneous direction. So if the object is curving, it's whatever the instantaneous direction of the velocity is. That's the angle. All right? And this force, once again, is perpendicular to these two. So we have another right-hand rule.
Oh dear, oh dear.
Okay, so let's do our next right-hand rule. Right down here. Magnetic force on a moving charge.
How many do we have in total?
We'll have, I think, 3. These 3 is all you really need.
Okay.
We might have another one, but you'll be okay. All right, so it's Q, V, B, sine theta. And that's the angle between these two. And our right-hand rule looks like this. All right, you ready?
Whoa.
All right? There's my magnetic field again. Here's my force again. But this time, this is now the velocity. Because remember, current is the movement of charge, right? So our index finger was already pointing in the direction of the positive charge velocity. The angle is the angle between these two.
Wait, so they're always...
Okay, this will not always be 90, and I'll show you that in a minute.
Oh, I'm thinking
But on the other
field
one, so
side.
it's perpendicular.
Those are not always 90 as well. Let's go back. I'll show you.
I don't know, but like she was recording the videos and like she just randomly started like.
Oh, is that the reporter that was started speaking gibberish?
Yeah, she started speaking. No, but she didn't have a stroke. They said it was just like something like neurological that she had.
Maybe it was a mini stroke.
All right.
It was a mini seizure.
Which way's the force on this wire?
The force on the wire.
All right, we're gonna do this.
Okay.
Ow. Oh wait, no. Out of the force.
Wrong hand.
Out of the board.
Okay, current this way, B field up, force out of the board. So our force on this would be out of the board, right?
Yes.
Okay, but what if my wire's like this instead? Okay, now everybody look. Your fingers go this way,
Hey, the velocity's that way.
but notice my angle here between these fingers is not 90 anymore, right? Well, you're okay. Which way's the force? It's still out of the board, right?
Just not as strong.
Why not as strong? Because my sine theta is now less than 1, right?
Yes.
Okay, what if my current goes like this?
It'd be really strong.
Current this way, B field that way. What's the angle between those?
I'm gonna say
0.
Because you're like 0.
Sine of 0 equals, sine of theta equals 0 in this case. So what's my magnetic force?
0.
Okay, it's 0. Okay? So, these, your B field and your velocity or current do not have to be in the same direction. Okay, so you can have an angle between 0 and 180. 0 and 180.
0.
0, 90, 180, 45, 63.
63
Can you try not to confuse me?
I try not to confuse you every day. Okay. So here you go. You ready? Here's my magnetic field. Here's my proton going this way. And here's my electron going this way. Okay, what's the direction of the force on my proton and my electron? Let's do this one first. Which way is the force on this one? Up. The force is up
There's a force be with you.
because the current is this way, or my velocity is this way. My B field's into the board, so the force is up.
Force be that one, the other one. Force be
Okay, now, on this one, what does your right hand tell you?
It tells you
Velocity up, B field into the board. It says the force should be to the left.
No.
But
It's an electron motion.
It's an electron. What does that mean?
Current is reversed a little lot.
Okay. All right, now, everybody, they will always, on the test, at least twice, ask you something about the direction of the force on moving charges, and they'll throw an electron in. Or they'll say an electron, so they know that you should know that that's negative. And negative means opposite direction, right? So my right hand says that it should be to the left, but it's an electron, so the force will be to the right.
What if we use our left one on the left?
Now, here's the deal. You have a couple of options, and you decide which option you want to use. Okay?
You can use both.
The option is that you could use your right hand for everything, but if it's negative, you just flip it the other direction, right? Or you can use your left hand for all things negative.
Just in the middle of the test, you're like this.
Yeah.
So why is it to the right if it's an electron?
Because your right hand says this way, but it's negative, so it's opposite. Okay? Everybody, you can decide. If you want to try your left-hand rule, it looks like this. Current up, B field into the board, so force is to the right. I personally like to use right hand and left hand. Some students do not like to do that. Some students always like to use the same hand.
You know, this is how I do it.
And there is more than one way to do the right-hand rule. There's this method that some schools will teach, that you do a palm method, and there's different ways. I teach you this way because this is the way that will help you when you get to Physics C, because we do something called a cross product, and that's how you do it. You stick your finger in the direction of the first vector, and you curl your fingers in the direction of the second vector, and that gives you the direction of the answer, okay, for a cross product. So that's the way I teach you. All right, it's a little bit harder to learn at first. Once you have it, it's a piece of cake. All right, let's get some more practice at this, because you need practice. Let's do this one. What if my magnetic field is this way? All right, here we go.
It's in the game.
Okay, here is my helium nucleus, otherwise known as an alpha particle.
Positive charge.
So therefore, it's a +2 electron charge, right? Don't be confused.
+2 electrons, that means it's
Yeah.
negative.
So that means no. Stop.
That's what he was.
Electron. When they say electron charge, they mean the magnitude of it, and then it's positive. So it's a +2 size of an electron charge.
Alright.
All right. And then I want you to do this one. Let's do this one. And there is a negative charge going that way. Which way is the direction of the force on the helium nucleus?
Wait, which way is the force?
Which way is the force on the helium nucleus?
Into the board.
Yeah, I'm sorry, I didn't write V down, did I? That's the velocity, and that's the velocity.
Into the board.
Yeah,
They're
into
all
the board.
Okay, helium is
Into the board.
up, B field, so into the board, correct? So the force on the helium nucleus would be into the board, right? Okay, what's the force on the electron, or the negative charge?
Okay. That way?
Also into the board?
No, it's out.
I don't even know. It's into the board as well.
This way,
It's out.
this way.
Left hand. Left hand.
that's it.
Negative charge.
Left hand.
Negative
Negative
charge.
charge.
Negatives to the left, right.
Ah! Negative. Opposite.
It took me forever to figure out how to put my hand there. When I finally did, I think I
You're like, ah! Oh. Redeem it? You need something? All right, everybody, if you use the right-hand rule for your negatives, you'll point this way, you'll say the B field is this way, and then you'll say it's out of the board, but since it's negative, therefore it's going to be into the board. Okay, if you use your left-hand rule, you'll say the current is this way, or the velocity is this way, B field is this way. Notice the angle is less than 90, right? And your thumb points into the board. So your force on this one is also into the board. Okay? Yes?
When you're doing a right angle, can you assume to make your index finger go into the obtuse angle, or you cannot do it?
You can, like for instance, what if I had a positive charge going, oops, sorry, what if I had a positive charge going this way? All right? What about this one? Positive charge going this way.
It's still into the ball.
Oh, past 90, right? Okay, but that's still the way it works, right? So the force is still into the board, the way I have it drawn. Now notice that for this positive and for this negative, that the forces are less than what their maximum value could be, right? Because their angle is not 90. Yeah, that this finger always points straight and you curl these. Okay. Right? Yeah, because I'll get students that'll do that and then they'll get it messed, they'll get it backwards.
Wait, what?
This finger always points straight and these are the ones that curl. Okay? Alright. I still don't think you know it. Let's try another one. Positive charge. Negative charge. Velocity, velocity.
Wait, it's coming out of the board, right?
Yeah, it is.
Force is down.
Then one put that.
Yeah, this way. Yeah. And then left hand pull.
Positive. Then the other one is
Hey, okay, but it's negative.
the negative one is up.
The negative one is up, positive one is right.
Yeah.
I didn't see it. Really
That's right.
Okay, this one. Positive charge. Velocity is, and it's positive, right?
So it's right.
And so it's to the right. So the force on this one is to the right. Okay, this one. Negative charge if you choose to use your left hand. Current or velocity. B field out. So the force will be up. There you go. Excellent. We're stepping into a spot where you really got to think. Okay? So, here we go. I have a capacitor. All right. I take a proton and I shoot it this way with a velocity.
What are those two things? Wires?
That's the capacitor plates. All right, now, my question to you is don't shout out the answer. I want you to discuss it with the people around you. Which way will the proton curve? Will it take this path and go straight through? We'll call that path A. Will it turn this way? Call it path B. Or will it turn this way? Call it path C. Okay, don't yell it out. Talk to your neighbors. Now, shh, quiet. In order to solve this, first thing we must do is decide which plate is positive. The one on the left?
Yes.
Okay. Here, let me get here. Here, the one on the left then becomes positive because it's attached to the positive side of the battery, right? It shares charge until it gets the same electric potential, right? Okay, so this one is the negative side of the battery, so it shares potential or shares charge, so it's the same potential. Okay, next thing is which way will the said magnetic field. Which way does the electric field now point?
From left to right.
Towards the right.
Okay, from left to right, straight across, from plate to plate, it's uniform and the same magnitude and direction all the way, right? Okay, now when a proton is in an electric field, Protons are
Positive.
positive. So a positive charge in an electric field gets a force which way?
With the field.
With the field. Parallel to the field. So this proton, when it's right here, gets a force that way. So it's going to start to curve. When the proton is here, it gets a force that way. So it continues to curve. When it's right there, it still gets a force that way. And the force is the electric force, which is EQ. The whole time. Okay, everybody? What do we call that path? What's the shape?
It's a parabola. Whoa.
It's parabolic trajectory motion, right? Just like driving a car off a cliff. Right?
As I am one to do.
Except
Zero.
our gravity in this case points that way, right? Okay. Hey. Shh. Come on. All right. So it curves this way. Okay. What if I take an electron and I shoot the electron through this way? What does it do? It's going to get a force that pushes it this way instead, right? Because remember, the forces in electric fields are always parallel. Parallel or anti-parallel, right? Either with the electric field for positives or opposite the electric field for negatives, right? Okay, now, magnetic field forces are not like that. Which way do magnetic field forces point?
Always like that.
Always perpendicular to the velocity and the magnetic field, right?
Well, perpendicular, because I mean they're not always.
The force is always perpendicular to the plane that these two are in, right? So this force is always perpendicular to this vector and this vector, and this one's always perpendicular to this vector and this vector, right? Okay, now pay attention. Here's my magnetic field. And now I have, we'll start with a positive charge. I have a positive charge that's moving this way with a velocity, and it shoots into this region of magnetic field. Okay, when it enters the magnetic field, right here, which way does it receive a force?
Down.
Yeah.
Velocity that way.
Down.
B field is this way. You almost got it. Okay, and then your thumb points. There you go. So the force is down. Okay, everybody. If you're running down the hallway this way, and somebody comes along and shoves you that way while you're running that way,
Shove it back.
yeah, you do. Newton says you shove them back. Nice.
But then you shove it.
But what happens to your motion?
You
It
purposely
changes.
It changes. You turn this way, right?
Oh, they shove you from.
Except you see it coming, so you jump towards them. So you
So your path turns, right? But now which way is your velocity? Everybody point. Which way is my velocity now?
Still the same.
Is my velocity still that way?
Well, I mean direction or velocity.
What is the direction of my velocity when I'm right there? Am I still just going that way?
No, you're going down.
I'm now going that way. Remember, velocity is always tangent to the path, right?
yeah.
Velocity is always tangent to your path. Okay, now everybody, tell me, what's the direction of the force now? Is it still down?
Would it be upper that way?
Inward.
Upper that way. It'd be up to the right.
It would be 90 degrees. So,
Perpendicular.
yeah.
Oh,
Velocity's this way, B field's out, so it's going to be
down.
this way. Uh-oh.
And so on and so on and so on, making a circle.
Okay, everybody, this is really important. Shh. This is really important. Magnetic field forces are not the same as electric field forces. Electric field forces are like gravity. They always point, well, at least in a in this situation right here. It's always going to point in that direction, right? Or that direction. But this one, it depends on your velocity. Now my velocity vector is changing direction. So which way is my new force?
That way.
This way. Okay, have you seen this before? Yes, this is uniform circular motion. Because the object is going to go, and if it was in a full magnetic field, it would go in a complete circle. But since mine is going to exit my magnetic field down here, then what will happen is when it exits the magnetic field, it'll just go straight from there.
That's only for.
Okay.
If the magnetic field's the same.
If the magnetic field was uniform everywhere and it didn't exit the magnetic field, it would go in a perfect circle.
Wait, so could you actually do that?
So, Ian asks, are we going to have to do circular motion? Does that look like circular motion?
Yeah.
Will we have to do circular motion?
Yeah.
Okay, so here we go. The sum of the forces equals ma. Force is towards the center, acceleration is towards the center. Okay, in a normal, non-magnetic problem, what's the next thing we usually do?
V squared over R for A.
We say, well, that's v squared over r. But what's my force that's causing this to go in a circle?
Whatever we had, it was breaking it or
It's
whatever.
magnetic in our case, right? It was friction or tension or normal force or something. But now this time, or gravity, thank you. But this time it's magnetic force. Do we know what that magnetic force is?
Well, we can calculate it.
QVB sine theta. So I have a QVB sine theta equals mv squared over r.
Is the V's the same?
Is the v the same?
Yeah.
Why, yes it is. One of those goes away. And in our case, what's my theta? Let's see, V's that way, B field's this way. What's that angle?
90.
90. So that's going to be 1. So I get, and this is the way they normally rewrite this. Let me just get rid of some of this stuff. It's going to reduce to that, right? And the way they normally write it in the book is they put the R by itself. R equals mv over qb. All right? This is the mass of my object. Could be a proton. This is the velocity of my object. Could be really fast if it's a proton. This is Q. Could be the charge of the proton then, right? And then B is the external magnetic field. And that would be the radius of its path. Okay?
What about? And M is that.
Now, riddle me this. What if this was a proton? So there you go. I got a proton right there. And now I take, and right next to it, I shoot in an electron with the exact same velocity. How will the path of the electron be different than the path of the proton?
Other way, and then.
Okay, will it look just like this? Just like this
Yeah.
one?
Assuming that they're not like attracted to each other.
Maybe different
Yeah.
mass. Okay, yeah.
Okay? They have the same velocity, they have the same charge, they have the same magnetic field, do they have the same mass?
No.
Ooh,
Lot
ooh, ooh.
smaller.
So what happens to the electron
Radius
path?
is smaller.
Ooh, the radius is going to be real small, right? It's going to turn real quick. Okay? Turns real quick.
Get me out of here.
Right. Okay, now, everybody, how do scientists measure things they can't even see? Like protons and electrons. They go, 1.6 e to the negative something or other coulombs.
My answer was not supposed to be said out loud.
All right, here's how they do it. They created something called a cloud chamber, and a cloud chamber was a box that had just the right atmospheric conditions so that, have you ever been outside and you see a plane go overhead and it's real up high and you don't really see the plane but you see the streak it leaves behind?
Yeah.
That's called a condensation trail or a contrail. All right. If you have the right atmospheric conditions inside this box, guess what? We can't see protons and electrons. Literally, we cannot see them ever because our eyes see with wavelengths that are between 400 to 700 nanometers long. That means we can't see anything smaller than that. Well, these things, protons, are like 10 to the negative 10. They're like 3 or 4 orders of magnitude too small to see. We physically cannot see them. So what do? We set up this chamber, and when a proton flies through here, it leaves a trail. Well, how do we tell anything about that thing? We just know that something we didn't see went streaking right through. We set up a magnetic field. When we set up a magnetic field, look what happens. As they go through, if I know that my magnetic field looks like this, and I have these pathways, I get one that goes like this, and I get one that goes like this, and I get one that goes like this. A, B, C. Tell me about those three.
A is the proton, B is the neutron, C is an electron.
I drew it so that they would match up to a proton, electron, and neutron. Because look, how do I know that doesn't have any charge?
It's going straight through.
It goes straight through, right? It's moving in a magnetic field. It doesn't change direction, so it must not have a charge. Okay? If it curves up, then that means it's going that way, B field in, so it's curving up. So that means it follows the right-hand rule, right? Notice that this one does not follow the right-hand rule. Right-hand rule says everything curves up, right? If it's going that way, B field in, it should curve up. This one follows the left-hand rule, so it's curving down, right? And we know that this one has less mass than that one. So I drew them so this one looks like an electron, a proton, and a neutron. But could they be something else? Yeah, we don't really know for sure from this, but it does tell us the charge, right? Okay, our next thing is, all right, let's say that I have this proton going straight through. I'm sorry, proton turning up. All right? Here's my magnetic field. The proton is going upward. I don't want the proton to go up. I want the proton to go straight through. I want the proton to follow that dashed path. All right, now there's two ways. Number one is I could make a magnetic field in the opposite direction to cancel the original one out. I don't want to do that. I want to do it with that.
Electric field? Ah.
How would I set up my capacitor plates to make that go straight through?
The negative plate at the bottom, the positive plate at the top. Why would you kill us like this?
I would make a negative plate and a positive plate because the positive plate would repel it and the negative plate will attract it, right? And my electric field is this way.
I hope we all have to do a lab. Oh my god.
All right, now, this is on your e-homework. Okay, when the proton is right here, traveling to the right with a velocity, what's the net force on it if it goes straight through?
0.
0. What force is going up on the proton?
Whatever the positive.
The magnetic force, right? What's the force pushing it down?
Electric force.
The electric force. Okay, now everybody, these are called crossed electric and magnetic fields. Because my magnetic field is this way, and my electric field is...
Word.
They're crossed, right? Right? They're like this, right? They're crossed at a 90-degree angle. My electric field is down, my magnetic field's into the board, 90-degree angle. That's called crossed electric and magnetic fields. And here's the really cool thing. If you tune them just right, then these two will equal out and it'll shoot straight through, and that provides us with a really cool thing. The sum of the forces equals 0. That means the magnetic force equals the electric force. How do I calculate my magnetic force?
What we have there, that thing.
I got QVB sine theta. How do I calculate my electric force?
KQ.
It's not a spherical charge distribution.
Okay.
EQ, right?
Q's cancel.
Hey, look at this. The Q's cancel. And assuming that I shoot it in at a right angle, which we generally will assume in this class, that becomes 1, and I'm left with this magical equation. V equals E over B. Now this V is velocity.
Isn't it E or B?
E over B. Alright, this is for crossed electric and magnetic fields. This is also called a velocity selector. Why is it called a velocity selector?
Because you can determine the velocity.
Because you can determine the velocity of what goes straight through. Because here's what they'll do. They'll put up a wall over here with an opening. And that opening's real small. And look what they do. They tune the electric and magnetic fields until it's the speed they want. And only that speed goes through. What happens if you're going too fast? Which changes? Your electric force or magnetic force?
Magnet.
Does everybody see that your magnetic force depends on your velocity, right? If you go too fast, then your magnetic force gets too big. And you'll curve, well, either down or up. In our case, up, because I have a positive charge.
Yeah.
So if you go too fast, you'll curve up.
And so
If you go too slow, you'll curve
down.
down. If you're just the Goldilocks right speed, you'll go straight through, right? And it doesn't matter what the charge of the object is? No, because the charge canceled out. So all particles that have the right speed and that are charged will go straight through this thing. It's pretty cool. So sometimes students will ask, well, how do they know that protons and electrons exist, and how do they move them around to do anything with them?
It's that.
Here's one way that you can shoot these things through an opening and you know exactly how fast they're going, right? And then if you shoot them through a magnetic field, you know whether they're positive or negative, right?
Electric field.
And we're going to extend this idea into what's called a mass spectrometer on, when will I see you next? Friday?
Yes.
On Friday.